Ugh. Getting these things out of a string is a ball ache, or I should say a thumbnail ache. So after Bill and I live streamed the theoretical side of this, there's the simulation of the current drive, LED current drive. It's a classic circuit, not super complicated. This will allow me to run a string of 37 LEDs, which is what this Christmas light string had. 37 lights in series times 3. There's 2 other bundles there. None of them worked, so I've untwisted this one, and I'm gradually putting an LED in each socket, making sure they're all in series in line. So I'm keeping to my left the cathode sides and to my right the anode sides, so that they all end up in series properly, which is what we have in this circuit diagram up here. 37 LEDs in series. White LEDs have a nominal forward voltage drop of 3.2 volts when driven by 20 milliamps. I'll probably use, I've got a few different types of MOSFETs kicking around. Just for simplicity for this experiment, I'll use through-hole parts and solder them onto a bit of proto board. Probably use an IRF 830 here, and 33 ohm quarter watt resistor should be enough. 20 milliamps through 33 ohms is not a lot of power dissipation, so it should be totally fine. So have to be careful to get these exactly oriented right. LEDs, as you may know, you should know, are diodes. That means current only flows in one direction, from anode to cathode. I'm keeping the anodes on my left side, the cathodes on my right, so they're all in series correctly. This one, and unfortunately the tabs on the lamp sockets, this originally was made by Philips. I was kind of hoping they were all polarized and oriented exactly the same, so I could just take all the sockets out and put a bunch of LEDs in them and just plug them in. Unfortunately, I have to do them one at a time because they're oriented randomly. So this one has the tab on the cathode side. So I've got a big bag of LEDs here. The cathode is always the short lead on an LED. Anode's always the long lead from the factory. And if you can't tell, you can also look. You can see the lead frame, a thin bit of metal and a broad bit of metal with a cup which has a reflector that the chip is mounted in. The broad one with the cup that the chip is mounted in is always the cathode. And then in every LED I've ever looked at, and every data sheet I've looked at least, the broad one is the cathode, the thin one is the anode. Whew. Well, I finally got all that together and got the LEDs in the string, so you can see all the 37 daft 3-volt light bulbs there, and the LEDs are actually lit up and working. So what have we got here? Let me show you the setup. So I have this board, let me very carefully lift it and show you, has a bridge rectifier, a couple of capacitors for some smoothing, and the current limit circuit. I only put the caps there because I don't want the LEDs to flicker. I want the caps to charge up on the rising of the mains voltage and stay charged long enough to be able to discharge through the LEDs and the current source, so that we keep a constant current. There's the current source circuit right there. That's the LEDs go all around a string from the positive side of the supply, anode to cathode, all 37 of them in series, back to the drain of that MOSFET. The drain of the MOSFET, and the source goes to ground, or goes to the 0-volt rail through a current sense, a 33 ohm current sense resistor, and that is picked up by the base of that little transistor there, which is a BC547, and that's the emitter is connected to the negative supply rail as well, so that if the current drives that sense resistor beyond the 0.65 volt drop of the PN junction in that transistor, it starts to turn on. And then the collector pulls the gate, is connected to the gate of the MOSFET and pulls that low to start to turn it off, and that's how it regulates current. The gate is biased on through a 22 kΩ resistor to the drain there, because the drain voltage always remains, you know, somewhere around 50 volts or whatever at full mains voltage. If I've got 120 coming in and it's rectified, I have 170 DC and drop through 118 volts across the string of 3.3 volt, 3.2 volt LEDs. We end up at the drain at being about 52 volts, and so that's why we can tap the gate drive off of the drain. So all of that comes back through the meter. You can see I'm currently pulling 21.4 milliamps at full output. And the setup here, just so I'm not running off directly off mains, I have an uninterruptible power supply that's currently running on batteries, and that is feeding into my Variac, which allows me to specify where I'm at. And so it's at maximum right now, which is 130 V. I can dial this back down, and as I turn it down, you can see the current does actually drop somewhat with decreased mains input voltage. And I can go all the way down to where the current source is no longer trying to pull 20 milliamps. It's just doing whatever is available, and the LEDs are starting to flicker. If I go right down to where they're barely lit, let's just bring it back a little bit. So they're just lighting up right there. Just lighting up, and we're not even registering 0.1 milliamp on the meter. Let's go to the 2 milliamp range. Yeah, we've got about 0.03 milliamps there, and they're just barely lit, as you can see there. So this has, LEDs have quite a dynamic range that you might not expect, but this whole thing works pretty good. Now, looking here, I'm on the Variac at where? At about 60 volts for the LEDs to be just barely lit. I'm looking at the yellow trace on the scope here, where it rectified about 96.8 volts. So even below the 118 volts of the LED string, they do start to conduct. It's not a square VI curve. There is some curve to the curve. So let's start bringing that up again to where they're getting a bit more steady and bright. And at 10 milliamps, we're looking at a rectified 128 volts peak, 110 volts zero to the trough. Let's bring that waveform up so you can see it. So it's kind of a weird waveform. It's not what you might expect from rectified sine wave mains, but mains can be dirty. But this is actually coming out of a UPS. So let's go up. Okay, so we're driving at 20 milliamps, and now we have this interesting waveform here, which I'm triggering on here. At this point, I'm at the 112 volt output setting on the Variac, and we're actually getting 171 volts peak. So this is actually very typical of rectified 110 mains. And what's not typical about it is this stair step. The UPS is not a sine wave inverter. It uses a modified sine wave, so it's just switching on a stair step and then off, and then dead time, and then a negative. And so on the positive cycle, it's basically instantly charging our caps and delivering that 171 volts peak. And then as it goes into the negative cycle, the capacitors are discharging through the LED string and the 20 milliamp current sink. And so that's why we get a linear discharge instead of a sine wave or an exponential sort of curve, because we're not discharging through a resistor. We're discharging through a constant current circuit. And if you charge a cap through constant current or discharge through a cap through constant current, you get a linear slope. Just like if you put a fixed voltage across a fixed inductance, you get current rising linearly. And, you know, caps and inductors are the inverse of each other. So that's at 20 milliamps. Let's see if we can push this further. I'm going to dial that right up. The LEDs don't really get any brighter, which is what I'd expect. We're now at a maximum. We're pushing at about 22 milliamps. And there's also some current limit kicking in to a degree, because the MOSFET that's driving this is an IRF 830. The IRF 830 has a reasonable on resistance, but of course the whole MOSFET is being used as a variable resistor, and so it is dissipating about 1 watt of energy right now. So it's warming up a little bit. Nothing crazy. It doesn't seem to need a heat sink, but the result of that is it helps stabilize the current. So let's bring the trigger up here. So we now have a little bit of a spike on the front end of that, and then a shelf, and then our discharge ramp, and we're peaking out at 206, 207 volts there, and the LEDs are behaving quite nicely. They're nice and bright, but not too bright. They're in a safe operating zone for LEDs. This whole thing works. So the next phase, of course, is design a printed circuit board and make 3 channels and add opto isolators so I can do remote control of the 3 different channels, maybe pulse width modulation, brightness control, and things like that. But that's the basic setup. Isolated UPS through a nice variac, rectified and filtered mains, LED string down to the drain of the MOSFET, which is in the current control configuration. So that's it. That's how to renovate and make a better LED light string that's far superior to what you would just buy at Home Depot.